So we shall begin once again that just now we have seen that actinide elements, they are only 4 in number. They do occur naturally. Rest all other elements, that is from atom number 93, neptunium to lawrencium, they are synthesized artificially, or these are named as man-made elements. So these elements which are present after uranium, these are the artificial elements. We have also seen that when the element that is synthesized artificially by nuclear bombardment, then the names were given from the names of the planets. Some elements were given the names of the areas or the regions where these elements are invented, and certain elements were given the names of the scientists, and these elements are named after the names of the scientists. This we know. So only 4 members are naturally occurring, and remaining all other members are man-made or artificial elements. This we know. Now, if we look at the electronic configuration and the position of all these elements in the periodic table, similar to that of the actinide elements, because in the beginning it is very easy to understand what is the exact position of these actinides, similar to that of the lanthanides. So you have to take your notebook and we have to write again the electronic configuration of all these elements. I'm giving information that the electronic configuration that we are now going to study, this electronic configuration with the name of the element with respect to exact atomic number, that will enable you for the clear understanding of this topic. So the entire series with respect to atomic number and the electronic configuration, that is very important for the further study of these actinide elements. Now just see how the position and the electronic configuration of actinide elements is there that we have to study. First of all, we shall see in brief the position of lanthanides. It is very easy because here we have seen the hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. So this is a 6th period and this is a 7th period. Francium having atom number 87. After francium, atomic number 88 is of radium, which is from second A group of the periodic table. And again here a series of elements from atomic number 89, actinium, to lawrencium, atom number 103, that begins. So how can we assign the position? The 6th period and 3rd B group is for the lanthanide elements, 3rd B group and 6th period. And after 6th period, this 7th period which starts with francium, that is a alkali metal, first A group element, and after first A group, that is atom number 87, 88 is of radium, from alkali metals from second A group, and the 3rd B group which starts with actinium, atomic number 89, which ends with the element lawrencium, almost 15 members. So how to assign the position? Again, just see here, you have to note this and keep this in a box, that the position of lanthanides, Ln stands for lanthanide, AC stands for actinides, 3rd B group, again 3rd B group, but the period number is 7. So this is a point of difference between the position of lanthanides and the actinides. You should keep these 2 parameters in a box so that it is very easy for the clear understanding and for attempting the MCQ type questions also. Now here, this is a position of actinides in both these groups, that is 4F or 5F series. The group number is same, but period number is different. Lanthanides are in 6th period and actinides are in the 7th period. So this we know. Now, take your notebook. We are going to work out. the electronic configuration of these elements. Now, you take your notebook, we are going to see how the electronic configuration can be assigned. So here the first point is a electronic configuration of actinides, for which you have to prepare the column like this. First column is of atomic number, you have to write in your notebook, then the symbol of the element, and then the observed electronic configuration. So first column is of atomic number, second column is of the symbol, one more column that we have to add here, the name of element, because you should be familiar with the names of the element, and then the observed electronic configuration. So you have to prepare these four columns. First column is atomic number, second column is of symbol, third column is a name of element, and fourth column is observed electronic configuration. I am again warning you all that you should remember and listen carefully and attentively the atomic number, the symbol, and the name of element, which is required for the further understanding of this topic. Otherwise, you will be in trouble. I am going to only teach you, rest things are left with you. So I'm not threatening you, but you have to remember all these facts: the atomic number, symbol, name of the element, and observed electronic configuration. So first of all, we shall finish these three columns, that is the atomic number, the symbol, and the name of the element. Once we get familiar with all these three parameters, then we shall study the observed electronic configuration. So atom number 89, symbol AC, you have to write side by side. Name of the element is actinium, which is a first member, and from the name of this element, the name is given to the series, that is actinide series. Then you have to write second member H. This is known as the thorium. Then atom number 91, Pa, capital P, small a. You have to write like this, protactinium. Then 92, this is U, name of the element is uranium. 92, 2 is of uranium. Then 93 is Np, small capital N, small p, name of which is Neptunium. This name was derived from the name of the planet, that is the Neptune. This is a artificial or man-made element. Then atom number 94, Pu, name of which is plutonium, name of the planet, that is a Pluto, from which the name is derived as a plutonium. Then 95, Am, name is americium. Name of the element is americium, as it is invented in America, USA, and hence it is named as americium. Then atom number 96, Cm, capital C, small m, it is known as curium. Name of the scientist Curie, Curie temperature, and from which this name is derived as a curium. Then atom number 97, Bk, name is berkelium. Then atom number 98, Cf, capital C, small f, name is californium. Name of the element is californium, which was invented in California, which is again a part of USA, from which the name is derived as a californium. Then atom number 99, ES. Name of the element is Einsteinium. Then atom number 100, capital F, small m, known as a fermium. Perhaps you might have heard Fermi gas model. Name of the scientist is Fermi, from which this name was derived as a fermium. Then 101, MD, name of which is a Mendelevium. Mendeleev is regarded as a father of periodic table, from which the name is derived as a Mendelevium, because Mendeleev, why he regarded as a father of periodic table? Because of his countless contribution in the building of periodic table. He was regarded as a father of periodic table, hence the name is derived from his name as a Mendelevium. Then last but one element is NO, small n, capital N, small o, is known as a Nobelium. That is Nobel Prize that is given for remarkable achievement in the research of chemistry. That is a Nobel Prize, and from which the name is derived as a Nobelium. And last element, that is 103, symbol is LR, Lawrencium. Symbol is LR, name of the element is Lawrencium. So now we are familiar with all these elements, that is actinium, thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, fermium, mendelevium, nobelium, and lawrencium. Now we shall proceed further with the observed electronic configuration. So before going to start with the observed electronic configuration of atom number 89, we have to arrive at the electronic configuration of the elements which are situated before actinium. So the elements which are situated before actinium. So francium having atomic number 87, radon atom number 86, and radium atom number 88. So you should remember, or you have to write in your notebook these three members. Just now we have seen that while studying the position of periodic table, the last element from first A group is a francium, which is present in 7th period, and after francium, in the second group of the periodic table, that is second A group of the periodic table, alkali metal, next element, that is the radium. This radon is an inert gas element. No question about the electronic configuration, as it is having completely saturated electron subshell. So after radon, francium is the next element. In terms of radon core, radon is an inert gas element. So if I write in a square bracket Rn, that stands for radon, total number of electrons are 86. Just we have to add one more electron for francium. So the next choice for incoming electrons will be 7s. Hence I can write only 7s1. So radon 7s1, that is the electron configuration of francium. Now come to next element. Again, in terms of radon, we have to add two more electrons. That means like this. So we have written 86 electrons. 86 plus 2 is 88, which is the electronic configuration of radium. So the electronic configuration of radium atom number 88 in terms of radon core is Rn7s2. Now our series starts with next atom number 89. Now at atom number 89, again there are three electronic subshell. are there. Which are those? Again, 5F, 6D, and 7S, similar to that of 4F, 5D, and 6S, as in case of lanthanides. Here, 5F, 6D, and 7S. Again, we have to make a common statement that no question about the filling of the 7s orbital, which is filled at radium atom number 88. So we have filled 86 plus 2 is 88, just we have to fill one more electron. But different scientists were thought of whether the incoming electron enters into 6D or whether that electron enters into 5F. So different scientists were put forward different electronic configuration for all these actinide elements. But the electronic configuration that we are going to study here, this electronic configuration has been universally accepted. So if you refer some reference books, you may find some different electronic configuration of these actinide elements. Here, the observed electronic configuration is 5D1 and 6D1 and 5F0. So in some books, you may find 6D0 and 5F1, 7S2. This is electronic configuration of actinium. But here, this is the most probable electronic configuration that is the scientists thought of in the early day, and different scientists now rely upon that this is the electronic configuration that is the correct electronic configuration that is assigned to actinium. Now, after actinium, next member is atom number 90. In terms of radon core, we can write this as like this 6D and 7S. So no question about 7x. So 86 plus 2 is 88 plus 1 is 89. Now we have to add one more electron that comes in 5F level. So we are now familiar to feel how the electrons occupy either of these orbitals, and hence again we have to make a general statement that all actinide elements or all 5F elements, how many they have incomplete shells? That they have 3 incomplete electronic subshell. This should be noted. Now you have to write in your notebook the electronic configuration for actinium like this. For actinium, radon, 5F, 6D, 7S, 7S2, as we know, 6D1, 5F0, just now we have seen. You have to write this. Then you have to write for radon, 5F, 6D, 7S. No question about 7S, you have to write directly 7S2. Again, 6D1 and 5F1. Sorry. Here, I would like to show you, this is electronic configuration, that is the ideal electronic configuration. But if we see the energies of these 3 orbitals with their respective atomic numbers, here, this is atomic number 89, 90, 91, 92, 93. This is actinium, thorium, protactinium, uranium, and neptunium. You can also write in your notebook because this will enable you for the clear understanding of the disruption of electronic configuration. That is, the continuous build-up of electronic configuration is disrupted after actinium. Now, the 3 electronic subshell, just now we have seen that 5F, 6D, and 7S. If I draw these electronic subshell, then it can be shown as like this. This is an electronic subshell that is named as 7S. Then 6D, and this is a 5F. Here, this is electronic subshell that is a 5F. This is a 6D, and this is a 7S. What is the common conclusion that can be drawn from the energies of these different electronic subshell with respect to the atomic number? Come to actinium. We have seen when the 7s orbital that is filled at radium, here I have shown, because 7s orbital having low energy, but after this protactinium, atom number 91, 7s orbital is having high energy. Just see here. Before protactinium, 5f orbital having high energy, but after protactinium, 5f orbital is having low energy. And as we know that according to above principle, when the question of electron occupancy is there, the electron enters preferentially on the low energy orbital. This we know as a above principle. So this happens before and after protactinium. Now at actinium, as the two electrons are completely filled at radium, the next choice for incoming electron at actinium will be 6d1. So the 89th electron that enters into 6d orbital, because 5f orbital is high energy orbital, which is present after this. Now, just a minute. Now, here, after actinium, here the next choice for incoming electron will be for again 6d orbital, because when the orbital 7s is completely filled, next choice will be for 6d orbital, and hence the two electrons again enters into 6d orbital. Here I have shown, because 5f orbital is having high energy, that we have revealed from this energy level diagram. So occupancy of electrons that takes place in 6d orbital. So you have to write again 5f0 6d2 7s2. You have to write this 5f0 6d2 7s2. This can be shown from this energy level diagram, that after 7s orbital is completely filled, next electron at thorium that enters into 6d orbital. Now come to this protactinium. So as we are moving to protactinium or uranium also, all the three orbitals having almost similar energy, one cannot distinguish whether the electron is actually entering into either of these orbitals. So as we move one step further at protactinium, we can write the electronic configuration as radon 5f 6d 7s. No question about 7s 7s2. Again here somewhat disruption takes place, and the electron now enters into 5f orbital. So 86 plus 2 is 88, plus 1 is 89, plus 2 is 91. Again here some disruption is there. So 5f2 6d1 7s2, 86 plus 5 is 91. So this is an absurd electronic configuration of protactinium. Now we are moving closer to this uranium, where all the three orbitals are having almost similar energy. Now come to uranium, radon 5f 6d 7s. No question about 7s. You have to write in your notebook 7s2. Again you have to write 6d1, because it is very close to 7s orbital, having just high energy than as compared to 7s, and 5f orbital is higher energy than 6d, but the energy gap is very small, as can be seen from this here. The energy gap between 6d and 5f, that is very, very small. So we can write for uranium the electron configuration as 5f3. So 86 plus 6 is a 92, which is electronic configuration of uranium. So you have to write 5f3 6d1 7s2, which is electron configuration of this uranium. If you have completed, then come to neptunium, radon 5f 6d 7s 7s2, again 6d1, and remaining electrons are to be added in 5f4. So 86 plus 4 is a 90 plus 3 is a 93, which is the electronic configuration of neptunium. So here again we have to refer the diagram where approaching after uranium the neptunium. Now after uranium, here 5f orbital becomes a decisively more stable at neptunium, and now the 6d orbital is having high energy as compared to 5f. Here 6d orbital is having high energy as compared to 7s, but after uranium 7s orbital is having high energy, 6d is having average energy, but the point here is that 5f orbital becomes a decisively more stable after uranium or neptunium or so, and now because this orbital is a low energy, and hence now the incoming electrons enters after neptunium into 5f orbital. So the electronic configuration for plutonium, we can write this as 5f6d7s. No question about 7s2. Again 5d0, sorry, 6d0. Why 6d0? See here, for atom number 94, here 5f orbital is having low energy as compared to 6d, and hence whatever electrons are there, those enters into this 5f orbital. So this is how the occupancy of electrons takes place, and hence 86 plus 2 is 88 plus 6 is a 94, 6d0. So this is the observed electronic configuration of plutonium. Now, plutonium, from plutonium onwards, the 6d orbital becomes empty. Come to americium, radon, 5f, 6d, 7s. Now we can write very easily 7s2, 6d0, and 5f7. So americium 5f7, 6d0, 7s2. After americium, curium, again there is some more disruption, because here if we try to write the electronic configuration, here there should be 8 electrons, but because of very small energy gap between 5f and 6d, one of the electrons is transferred to 6d orbital, which offer extra stability associated with completely half-filled electronics of shell. So you have to mark this by asterisk sign, because it has acquired extra stable electronic configuration, that is a completely half-filled electronics of shell. This was happened also in lanthanide series at atom number 63 europium, and we have marked that element also by asterisk sign. Now come to berkelium, 5f6d7s. No question about 7s. Again 6d0. As we move one step further, the energy gap between 5f and 6d again increases, and the incoming electrons now enters into 5f orbital. So 86 plus 2 is 88 plus 9 is 97. So berkelium 5f9, 6d0, 7s2. Now come to californium, radon 5f 6d 7s. Right? Californium, radon 5f 6d 7s. No question about 7s. 6d0 as usual, and whatever electrons are left, those to be added in 5f0. So here all the 10 electrons, they occupy the 5f orbital. So californium atom number 98, 5f0, sorry, 5f10, 6d0 and 7s2. Then radon, for einsteinium, radon 5f 6d 7s. No question about 7s. 7s2, 6d0, high energy after 5f, and whatever electrons are left, those are to be added into 5f orbital. So 86 plus 2 is 88 plus 11 is 99. Come to fermium, atomic number 100, 5f 6d 7s. Now no question about 7s. again 6d0, and 88 plus 12 is 100. So fermium, atom number 100, 5 of 12, 6d0, 7s2. You have to write very carefully that again it does not contain any electron in its d level. Come to Mendelium, atom number 101, radon, 5f, 6d, 7s. No question about 7s. You have to write directly 7s2. Again, no question about 6d, 0. And whatever remaining electrons, that is 13 electrons, are to be added in 5f. So now 5f orbital is short of only 1 electron, so as to complete it's completely filled electron subshell. So 86 plus 2 is 88 plus 13 is 101. Now come to nobelium, last but one element, radon, 5f, 6d, 7s. No question about 7s. You can write directly 7s2. Again 6d0. And whatever electrons are there, we have to write in 5f orbital. That is, as per this sequence, you have to write 5f14. So 86 plus 2 is 88 plus 14 is 102. That is a nobelium. And it is very easy. I think you can write directly this electronic configuration as like this. 7s2, 514. Now just see again. Here at nobelium we have written 7s2, 5f14. Now after the 5f orbital is completely filled by electron, now the next electron at 103, the next choice for incoming electron will be 6d. We have to write this as a 6d1, because when the orbital is completely filled, next incoming choice will be of 6d. So we can write the 103rd electron in 6d1. Now, what is a common conclusion that can be drawn from the electronic configuration? Just take a closer look of the electronic configuration of all these 5 elements: actinium, thorium, protactinium, uranium, and neptunium. You have to write in your notebook. That will enable you for the study during your exam time. All these elements, they do contain single electron in its d level, except that of this thorium. All these elements, they contain single electron. See here. Now what is a drastic feature after neptunium? Only at this curium, which contains a single d electron, and the last element, that is lawrencium, which contains single electron. The rest, all other members, they contain no electrons in their 6d level. So you have to write, while writing the electronic configuration of actinides, that all these elements up to neptunium contain single electron. I have told you already the reason why there is an unusual electronic configuration, and this usual sequence is again somewhat disrupted at curium. One of the electrons is lost to 6d level, and hence instead of 5f8 6d0 7s2, it becomes 5f7 6d1 and 7s2. So you have to mark this nobelium again by an asterisk sign. Why? Because nobelium is having completely half-filled electronic subshell. So the elements, that is a curium having atomic number 96 and nobelium having atomic number 102. These are the two members. They do display 5f7 and 5f14 configurations respectively. So you have to write the electronic configuration like this only. Again, I'll give you alert that only the first 4 members, actinium, thorium, protactinium, and uranium, these are the first 4 members, they do occur naturally. Remaining all the members, they do not occur naturally, but they can be synthesized artificially, that is from Neptunium to Lawrencium. These are the man-made elements which are present in actinide series. So only 1 minute is left. I would like to stop here. We shall begin with this topic, the next aspect, tomorrow also.